Okay, so the first two things, lab exam 3 is in lab this week. As always, if you can't make it to your lab or it's more convenient to go to a different lab, that's always fine. Just show up at whatever one works for you. And the second thing is quiz. I didn't look at how many we've done, but I think this is quiz 4. Is going to be this Wednesday at the end of class. So, be sure you skim through your notes for that. Anybody have any questions about either of these two things? Okay. Last time we started talking about rotational motion. We started with rotational kinematics. I introduced angular velocity and angular acceleration and talked about sort of going back and forth between the angular velocity and the velocity vector of a point, and then the angular acceleration and the tangential acceleration at a point. Remember doing that? Anybody have any questions about any of the homework problems I assigned? I'd be happy to go over any of those if anyone would like. Okay. Well, today we're going to combine that with the causes of rotational motion. So last time we did rotational or rigid body kinematics. We introduced the angular velocity omega, and we introduced the angular acceleration alpha. And then to relate, so for the angular velocity, we saw that the speed of an object is equal to the absolute value of the angular velocity times the distance from the hinge to the point that you're looking at. And you had to get the directions of anything from just thinking about the circular motion. And with the angular acceleration, we saw that the magnitude of the tangential acceleration was equal to the absolute value of the angular acceleration times r. And again, directions you had to get from thinking about circular motion. Now we're going to go on to rotational kinetics. And the idea is that we're going to combine kinematics, sorry. Combine rotational kinematics with the causes of rotational motion. One thing to notice is that there's a change that happens with rigid body motion. We didn't see this with particle motion, but notice that for rigid bodies, the location where a force acts matters. It affects the behavior of the body. And so the first thing we want to get straight is, well, the first force that we always deal with is just the weight. With particles, we never had to think about where the weight was acting. It just acts on the one place where we're treating the particle. But what about rigid bodies? Where do we treat the weight as acting? We're always going to treat it as acting at the center of mass, the middle of the object when you have like a rectangle or a circle or something. So the weight force always acts at the body's center of mass. Okay, and what we're heading towards is the big equation for rotational motion. Just like with particles, our big equation of motion was Newton's second law. You're going to see the similarities between Newton's second law and this one. I'm going to call it rotational Newton's second law because you derive it from Newton's second law. And it says that if you add up all the moments or torques, those are synonyms. You can use the word moment or torque. I'll define that later today. If you add those all up, that's equal to the mass moment of inertia of the body times the angular acceleration. This is like a rotational version of a force. And this is like a rotational version of mass. Okay, so you should see the similarities between this and F equals ma.
Is it in newtons though?
No, it's not. It's in Newton meters. And so before we can use this equation, I have to define the two things that you haven't done calculations with before. So before we can use, I'm going to call it Rn2L, rotational Newton's second law, we need to define moments, otherwise known as torques. And the moment of inertia. This is the one that's like, you know, the moments or the torques is the rotational version of a force. And moment of inertia is the rotational version of mass. Okay, so let's start with moment of inertia. Just like when we were doing this with particles, we started with mass. So this is the moment of inertia. And we'll always denote it with a capital I. And it's a positive scalar quantity, so just a positive number. That's large if an object is hard to rotate around its hinge. and it's small if the object is easy to rotate around its hinge. So a high value of the moment of inertia happens when mass is distributed far from the hinge and a low moment of inertia is when mass is distributed close to the hinge. Okay, so let's think about this intuitively. I think this is a good thing to keep in mind when you're thinking about the meaning of moment of inertia. So think about like gymnastics or diving. And think about someone doing like a double flip in the Olympics or whatever. And you'll see them, their bodies will be in various different positions as they do their flips. But let's think of two possibilities. So the first one is like you'll see people do their flips in a position like this, where, okay, their center of mass is like in here somewhere. So we'll think of their center of mass as the hinge. Okay, so their knees are pulled up as tight as they can, their arms are pulled in, and they're flipping around this way. Okay, and then the other thing you'll see is people doing flips in a position like this. And their center of mass is right around here somewhere. So this could be two pictures of the same person. It's not that there's a difference in mass between these two cases, but think of how close or far away from the center of mass, from the hinge, all of this person's mass is in these two cases. In the one on the left, this person has their mass pulled in as far as they can, as close as they can to their center of mass. In the second case, they really have everything spread out about as far as they possibly can from the center of mass. I guess they could spread it out more if their arms were over their head, but other than that, this is about as spread out as you can be. So think about the meanings of the moment of inertia and tell me, is the moment of inertia, for the one on the left, is the moment of inertia high or low? Low, yep. And so is it easy to rotate in this case on the left or hard? Easy, yep. And over here, so now everything's spread out. So the moment of inertia is high in this case. And so is it hard or easy to rotate in this position? Yeah, so this is hard to rotate. And so if you see somebody in the Olympics do a double flip like the one on the left, you know, they don't get as many points for it as if you see them do it the way in this position on the right. The reason is the harder it is to get your body rotating, the more power you have to have, the higher up into the air you have to get to complete, say, two flips, you know? And so with relatively little power, you can get the job done in this position, but you have to have a lot of power to get the job done in this position. And so you get your points according to that. Now think about the relationship between this idea and the mass for particles. Okay. Do you remember what I said the definition of mass was for particles? So mass is a resistance to acceleration, okay? Something with a lot of mass, it's hard to get it accelerating. The moment of inertia is a resistance to angular acceleration. If you have a big moment of inertia, it's hard to produce a big angular acceleration to get this thing spinning quickly, okay? If you have a low moment of inertia, it's easy to get the thing spinning quickly. The units for moment of inertia are mass times length squared. And so that means that the SI units are kilogram meters squared. Almost all of the calculations we're going to do are going to be with rectangles. And so here is a set of formulas for the moments of inertia for rectangles with hinges at various locations. So moments of inertia for rectangular shapes. With the hinges at various locations. So let's say that this rectangle has a mass m, and dimensions, I'll call this W for width, and I'll call this L for length. And here are the locations where, so you could have this rectangle have a hinge at any of these locations, and we'll be able to do this calculation. The first one is at the center, so I'll call that A. The second one is on the edges along the short, dimension, but in the middle along the long dimension. Do you see that? And I'm going to call these location B. So notice that it doesn't matter which one you have. Mathematically, it's the same. These are equivalent. Then the third one, here and here, those two are equivalent. I'll call that C and C. And then last is if the hinge is in the corners. Those are all equivalent. And I'll call that D. And the formulas for hinges in these different locations are, if the hinge is at A, then the formula is 1/12 times the mass times the quantity length squared plus width squared. The second one, if the hinge is at either of those two B locations, then the formula is 1/12 times the mass times L squared plus 1/3 times the mass times W squared. if it's at either of those two locations C, then the moment of inertia is 1/3 times the mass times L squared plus 1/12 times the mass times width squared. And then the last one, if it's at one of the corners, the formula is 1/3 times the mass times the quantity length squared plus width squared. And notice that, so they're getting smaller as you go in this direction and larger as you go in this direction. And you also might notice that, so the coefficient is 1/12 for either one of these sides where the hinge is in the middle. And it's 1/3 for either one of these sides where the hinge is at the edge. Okay, so that's how it determines, like, for example, for C, we're at the edge in the long dimension. So we're going to have 1/3 times the mass times the long dimension squared. And then we're in the middle in the short dimension. So we're going to have 1/12 times the mass times the short dimension squared. You don't have to remember that stuff. I'll always give you that stuff on tests and everything, but that is just a way to kind of make sense out of it. Yep.
So for B and C,
Mhm.
the length and the width, those calculations aren't inside the parentheses.
Yeah, they're not. That's right, because you have different coefficients for each one of those two. That's right. Any other questions right now on that? Yeah. Yeah, just if you had, like, no matter what the lengths and widths are for these, the biggest moments of inertia would be when the hinge is at the corners. The next biggest would be when the hinge is at those 2 points C. The next biggest would be B, and then the smallest would be when it's at the center. So it's always easiest to get this shape spinning if it's connected to the, okay, so if I put the hinge here, it's easier to get this thing spinning. I mean, my finger's kind of keeping it from spinning, but it's easier to make it rotate when the hinge is at the center than it is when the hinge is at the corners. One thing that's worth noticing here sometimes, and I think it does come up in a couple of problems. So notice, because L and W are squared in all these formulas, you can often treat the smaller dimension as 0 and still get okay results. So let me show you an example of that. So let's say that we have a board that has a mass of 10 kilograms. And let's say it has a length of 1 meter and a width of 1/10 of a meter. 0.1 meters. Okay. And it doesn't matter. Let's choose to calculate the moment of inertia with the hinge at the center. So we want to calculate, I'll call this A. So we want to calculate the moment of inertia about that point A, the hinge at the center. And then we're going to compare that answer with the width equal to 0. Okay. I mean, that seems like a pretty big, assumption to go from something that's 1/10 of the length to treating it as if it doesn't have any thickness or width at all, right? But we're going to see the results are pretty good because you square these values. So if we use that 1/10, we get 1/12 times the mass times 1 squared plus 0.1 squared and we get 0.83. We get 0.8416 repeating kilogram meters squared. And now let's do the same calculation, assuming that it doesn't have any width at all. Then that would be 1/12 times 10 times 1 squared plus 0 squared. And you get 0.83 repeating, which is pretty close, you know. Well, the reason for that is that when you have big differences in the dimensions, squaring it makes those differences vastly more different. So the width is 10% of the length in this, but once you square them both, the width squared is 1% as big as the length. Okay. So anyways, the short thing version of this is if you see questions that don't give a width at all, just treat it like 0. It means that the width is small enough that you can get pretty good results without it. Yep.
Does this only work if like the density is the same throughout the mesh?
Yes, that's a really good point. It does only work if it's homogeneous, same material everywhere. Any other questions? Okay, so that's the moment of inertia, and now we have to talk about the moment or the torque. And so let's say that we have some random object, and let's say that the hinge is here. And let's say that we have a force applied at this point P. And the force is like this. Okay. And this is not just like by chance that I drew this force perpendicular to this dotted line. At first, we're going to need this force to be perpendicular to the line between the hinge and where that force is. Okay. So now if the force is perpendicular to the line from A to P, then the moment produced by that force is equal to plus or minus the magnitude of the force times this distance d here. And then how do we know whether it's if it's positive or negative? Well, you have to think now, would that force, if this hinge was at A, would that force make it rotate clockwise or counterclockwise around A? It's positive if it would make it rotate counterclockwise. And negative if it would make it rotate clockwise. That's the same sign convention we used in the last class for rotational kinematics. So the way I have this drawn, so for that force, you can imagine like taking a hammer and tapping this object in that direction, and it's free to rotate around that pin A. Would tapping this object in the direction of F make the body rotate clockwise or counterclockwise around A? Clockwise, and so in this case, that would be negative. Okay, so first multiply out the numbers, then think about clockwise or counterclockwise to put the sign on it. The intuitive idea of the moment or the torque, I think the easiest way to think of it is think of trying to turn a bolt that's kind of stuck. So say that you know you can apply 100 newtons of force to this wrench. Well, let's think of applying that 100 newtons of force here, and then think about applying it here, and then think about applying it here. Okay? If you're having trouble turning this thing, which of these three forces, which of these three locations would be the best choice to apply that force to make this turn? The one out on as far away as possible, right? And you probably, plumbers have these gigantic wrenches so that they can apply these big torques on things. You could maybe, if it's not too stuck, you could get it turning by applying that force at the middle. That would work okay. But you probably have intuition that like, if you just stood over it and pushed down on it like this, it would never turn. If you could apply 1,000,000 newtons and it would never turn. Eventually, the head would just strip right off this bolt and it still would have never turned, And so from that formula, you can see the importance of that distance. It's not just that we're multiplying by a force of 100 newtons, but that distance that we are from the hinge is also important. But it's also important, besides that distance, it's important that that force is perpendicular to that distance. Okay? Like, what would happen if I apply this 100 Newton force straight, pushing straight to the right? That wouldn't turn this either. Okay? Because I'd be applying a force that's not perpendicular to that line from A to P. Okay? Okay, so let's do an example. So first, let's say we have this rectangle and the hinge is here. I'll call it A. And then here we're applying a force this way of 30 newtons. And I'll give this some dimensions. Let's say that this is 1 meter. And this is 1/4 of a meter, 0.25 meters. And we want to know what's the moment produced by the 30 Newton force. Well, first we have to figure out whether the force is perpendicular to the line between A and P. Okay, so I'm just going to draw the line from the hinge to where the force is applied. So is that 30 Newton force perpendicular to that line? Yes. And so we know we can calculate the moment as plus or minus the force times the distance, which is 1. And now we have to think, would this 30 Newton force make this body rotate clockwise or counterclockwise around A? Clockwise. And so it's negative. And so our answer here is 30 Newton meters. Oh, I didn't give units yet. Well, now I'll give them. So the units for moment are, well, you can see it just comes from this formula. The units are, newtons times meters. So this is always units of force times units of length. And so the SI units are newtons times meters. And I didn't write the negative in here, but remember to put that negative here in the answer. So for this example, the answer was negative 30 Newton meters. Anybody have any questions about that? Okay, so kind of the last question is, what happens when the force is not perpendicular to the line between the hinge and where the force is applied? So what happens when the force isn't perpendicular to the line between A and P? Well, without changing the problem, without changing the behavior of the system, you can always move the force anywhere along its line of action. And so all we're going to do in that case is move the force along its line of action until it's perpendicular to the line from A to P. Okay, so for example, say this is the body and this is the hinge. And let's say that there's a force applied this way at that location. Okay, so let me just sketch this line in. Oh, computer. So are those two lines perpendicular? No. So what I'm going to do is the line of action is like, think of it as the infinitely long line that the force lives in. Okay? And you can move it anywhere along this line without changing the behavior. And so we're just going to move the location of this force to here. And now that force is perpendicular to the line from A to this new P. Those are perpendicular now. Okay, let me do an example with some numbers and stuff. So let's say we have this rectangular plate. And let's say that our hinge is at the center. And there's a force applied up here of 20 newtons. And a force applied here of 10 newtons. And the dimensions, let's say that the width is 1 meter and the height is 3 meters. And we want to calculate the net moment, the sum of the moments. Okay, well, you can see that the line from A to where this 20 Newton force is applied is not perpendicular to the force. And you can see that the same is true with that 10 Newton force. It's not perpendicular to that line. So we're going to have to move these forces along their lines of action. Okay, well, the line of action of the 20 Newton force is horizontal like this. The line of action of the 10 Newton force is vertical like this. And so I'm going to reposition those forces that 20 Newton force, I'm going to move, so this is A. I'm going to move that 20 Newton force to be here. And I can do that because that's along its line of action. Everyone with me on that? And I'm going to move the 10 Newton force vertically along its line of action to here. And now these are perpendicular to the line from the hinge to where the force is applied. And so now for the 20 Newton force, that's plus or minus, the force is 20 Newtons. What's the distance from that 20 Newton force to A? 1.5, yep, half of the length. And would that 20 Newton force make it rotate clockwise or counterclockwise around A? Clockwise, so negative. And so this is negative 30 Newton meters. And then for the 10 Newton force, that's a force of 10. What's the distance from A to where that 10 Newton is applied? 0.5, yep. Would that 10 Newton force make it rotate clockwise or counterclockwise? Still clockwise. And so this one is negative 5 Newton meters. And so the net force is just the sum of those two. So negative 30 minus 5, so negative 35 Newton meters. Any questions about that? Okay. Well, now that we know how to treat moments, we know how to treat moments of inertia. Now we can go to the rotational version of Newton's second law. So let's do a full example problem. So let's say that there's a board connected to the wall by a hinge. And let's say the length of this board is 2 meters. And the mass is 10 kilograms. What's the angular acceleration of this beam? Well, I'm going to start first with a free body diagram. What forces are acting on this? Well, there's a weight force acting. I'm thinking of like weight acting towards the bottom of the page, so weight is acting this way. And it acts at the center, so there's a force of 10 times 9.81, so 98.1. Okay, and now look around the boundary for where the body contacts the surroundings. The only other place is here, and you should always draw the force at the hinge in like this, even though it's not going to affect the moments. And we'll talk about that in a sec. So I'll call this Rx and Ry. We just don't know, it's an X component and a Y component, but we don't know what those are, so I'm just putting them both in there. Okay, so let's start by calculating the moment of inertia. The hinge is over here at this dot. Notice that that's at the edge along the long axis and in the middle along the short axis. Okay, I didn't even tell you what the short dimension is, so we're just going to treat that like 0. But the fact that we're all the way at the edge of the long dimension means I is equal to 1/3 times the mass times the length squared.
We're not gonna do the width on this one.
The what?
We're not gonna calculate the width. 'Cause it's-
Right, we don't, yeah, it just isn't going to affect anything very much. We're just assuming that it's small enough that we'll get a good number with this. And so this is 13.3 repeating kilogram meters squared. And now we have to calculate the moments. Both of these two forces are acting at the hinge, which means that the distance is 0. Okay? So the moments produced by those forces are just always going to be 0. The forces at the hinge never are going to produce a moment in these. Okay? But what about the weight force? So that one's equal to plus or minus. The force is 98.1. What's the distance from the hinge to where that force is applied? 1, yep. And would a force downward like that make this body rotate clockwise or counterclockwise around the hinge? Clockwise, so we want the negative. And so this is negative 98.1 Newton meters. That's all the forces, and so we can add them up, and the net moment is 0 plus this, so negative 98.1. And now we can put it into the rotational version of Newton's second law. And it says negative 98.1 is equal to 13.3 repeating times the angular acceleration. And so the angular acceleration is negative 7.36 radians per second squared. Any questions about that? Okay. From this point, if I had also told you at this instant what the angular velocity is, we could use what we did in the last class to figure out what the velocity vectors and acceleration vectors are at various points on this body. Okay, so you'll have to do that in some of these problems eventually. Well, I think I'm going to stop there. Anybody have any questions before we stop? I'll give you a few problems to do that are just a lot like these, and then I guess we have one more class on Wednesday, and that's it.